this lecture, we continue with the topic of solid state. In the previous lectures, we have discussed about the possible crystal structures, arrangements, geometries, the types of unit cells, examples. This is already what we have seen. Now, the structures of ionic crystals we have to discuss. Different types of ionic compounds will exist in different types of crystalline structures. Ionic structures of ionic crystals. So, in this we discuss about the crystalline structures of cesium chloride, sodium chloride, calcium fluoride, lithium oxide, zinc blend, rutile, Al2O3, perovskite, diamond. All these most common examples. In what kind of crystalline structures that they exist, which positions, what is the type of the lattice, which ion will form the lattice, which ion occupy the void, and what type of void that ion occupy, whether will it occupy a tetrahedral void or octahedral void. Then based on that, what is the density of the crystal, what is the packing fraction in the crystal, and what is the coordination number of each ion in the crystal. As a result, finally, what properties that the crystalline structure the crystals will acquire. All these details we have to discuss, and in the most of the cases here, what all we have in the syllabus is most of them are face centered cubic lattice that they have, except the cesium chloride, Al2O3, except this. Most of them, whether it is sodium chloride, calcium chloride, lithium oxide, zinc sulphide, diamond and all, their lattice is FCC lattice. Of course, here diamond is not an ionic crystal, but just these are all ionic crystals, but diamond also we have to discuss, even if it is not what you call the ionic crystal. Now, in all these ionic crystals, what is the basic form of the lattice is first we have to see. Then what are the types of voids that it will likely to have, and in which type of voids that the other ion will occupy, and as a result what are the changes in properties, what is the packing fraction, this all we have to see. But before going to that, the basic principle of radius ratios is what we have to discuss. Meaning is, this ionic crystals, as we told here, one of the ion, mostly anion, will form the lattice, and other ion, mostly cation, will occupy any one or both types of voids, that is tetrahedral void or octahedral void. So, for example, NaCl, the anion chloride ion will form the lattice, sodium ions occupy the octahedral voids, and in the case of zinc sulphide, sulphide ion will form the lattice, zinc ions will occupy tetrahedral voids. Okay. So, like this, one of the ion will form the lattice and the other ion will occupy the lattice. In this case, MgAl2O4, if you look at it, oxide ions will form the lattice, magnesium ions and aluminum ions, they will occupy different voids. One occupies octahedral void, one occupies the tetrahedral void. In the diamond, carbon atoms will form the lattice, carbon atom itself again also will occupy tetrahedral void. So, like this, of course, as already we told, this is not a ionic crystal. So, its discussion is something different, but all these are ionic crystals. One of the ion, mostly anion, will form the lattice, either BCC type or FCC type lattice that it will form. The other ion, that is mostly cation, like in this case I told it is sodium ion occupying octahedral void, zinc ion occupying the tetrahedral void. Here both octahedral and tetrahedral voids that the ion will occupy. Now, the question is that whether the other ion, that is cation in general, sometimes even it may be anion, if one of the ion forms the lattice, the other ion will occupy which type of void, whether it is octahedral or tetrahedral or both, depends on what condition. It all depends on size of both anion and cation. Suppose if anion will form the lattice, then the cation to occupy an octahedral void or tetrahedral void, it depends on size of both anion and cation. That is, we determine with R plus by R minus. This is what we call radius ratio. It all depends on the radius ratio of the cation to anion. If the radius ratio is something lies between 0.414 to 0.732, then the void that it occupy is octahedral void. That means ratio of size of cation to ratio of radius of cation to anion, if it lies between this range, then the hole that is formed is an octahedral hole. So, the other ion will occupy that. I mean, that size of that cation is sufficient enough to occupy that particular octahedral void. But instead, if R plus by R minus is between 0.225 to 0.414, then it occupy tetrahedral void. So, it all depends on the radius ratio. Now, why the cation anion radius ratio lies between 0.414 to 0.732, that will give you then the ions will occupy octahedral void, otherwise it will tetrahedral void. And how do we decide that? That is all on the geometrical parameters. For example, if you have three ions like this will form a lattice, then here you have a particular ion, then the size of the, suppose three ions are like this in a two dimensional pattern, if you look at it, then here you have got a vacant space, this is a trigonal void. Now, the ion that should be, the ion that should occupy this space should be sufficient enough in radius that only it exactly fits over here. Either it exactly fits or little less than that, but definitely the size of the ion, this is, suppose if these are anions, these are negatively charged and this is positively charged, then this positively charged cation will occupy this void space. The size of this positively charged cation must be sufficient enough to fit it over here. If the size of this cation is larger than this, that means radius of this cation, if it is more than the radius of this void, then that cation will not fit into that space. So, the size of the cation should be sufficient enough to fit it over here, right. Then the radius of this particular empty space, void space, depends on what? Obviously depends on the size of these three anions that will form that particular void. If these three are bigger, then this void also bigger. If these are small, then this is still smaller. So, it all depends on the radius ratio, that is radius of anion to radius of cation to radius of anion. So, overall it depends on the size of both cation and anion. But instead, if the void is formed by these are the three, and another 3 if you keep it over here like this, then here this void formed is octahedral void, and here if you take this third layer, then this will give, now it will give a tetrahedral void. Size of octahedral void obviously will be more than the size of the tetrahedral void. So, depending on that particular size available in the void, the ion to occupy should have that particular size. Now, how do we determine this radius rules, radius ratio, and how these ranges we have given, that we will look at in the slideshow. Now, let us look at this. What is this radius ratio? How do we measure? And on the size of the anion and the cation, or how do we describe? This is a minimum ratio of radius of cation for various coordination numbers. Here in the ionic crystals, coordination number means the number of oppositively charged ions that are in contact with one particular ion. For example, if you take the case of sodium chloride crystal lattice, which we are going to discuss later, how many sodium ions are surrounding one chloride ion? That is what we call coordination number. And in case of a ion occupying tetrahedral void, means one particular ion, say cation like zinc ion occupying a tetrahedral void. So, what does it mean? Tetrahedral void is formed by 4 sulfide ions. So, 4 sulfide ions are in contact with one zinc ion. So, the coordination number for zinc is 4. So, in case of a tetrahedral void, in case of an ion occupying tetrahedral void, the coordination number is 4, and in case of ion occupying octahedral void, the coordination number is 6. So, like this. Now, coordination number 3. Coordination number 3 is something like this, that 3 blue spheres are in triangular shape. Now, that is a triangular void. The yellow sphere is at the trigonal void formed by 3 mutually touching blue spheres, right. Now, this the line joining of those 3 mutually touching blue spheres will give you a triangle, and side of the triangle is nothing but equal to 2 RA, right. That means radius of anion. RA stands for anion, radius of anion. Now, each sphere having a radius RA, then one side is equal to 2 RA. The next is, this is the yellow color is radius of cation, blue color is radius of anion. So, that if you look at it, now this black line that is drawn from a center of the yellow sphere to the center of the blue sphere is sum of the radius of cation to anion. Okay. Now, this is the radius of cation to the empty space. That center of the cation, if you take it as 0, and center of the anion if you take it as A, then the length is OA, then this is OB. Now, this angle if you take it, then the angle AOB is 30, angle AOB is 30. So, OA by AB, OA by AB is equal to RC plus RA by RA, that is equal to secant 30, which is equal to 2 by root 3. Okay. Or radius of cation to radius of anion if you take, it is 2 by root 3 minus 1, that is equal to 0.155. That means, if the radius of cation to radius of anion is 0.155, then coordination number will be 3. Or in other words, if you are having a coordination number 3, then in that case radius of cation to radius of anion will be 0.155. Finally, the meaning is, if you are having 2 spheres with the radius ratio of 0.155, then it will form a triangular void and the cation will occupy the triangular void. Next, we will see the coordination number 4. This is what I was trying to tell you. This is in the case of the this is what is the case of a tetrahedral void. Now, in this if you look at it, 3 blue colored spheres and 1 white colored broken line sphere. Those 4 are mutually touching spheres. That empty space in between left is in a tetrahedral geometry, or the 4 spheres, 3 blue colored and 1 white broken lines is the one that is in the tetrahedral disposition. The yellow colored sphere is occupying that tetrahedral void. This is something like this. So, the 3 white spheres and 1 red sphere. The red sphere is occupying the tetrahedral void. So, it is the 4 spheres of the 4 corners, then this is space center, then this is a tetrahedral void. That red colored ball is considered to be, as in the previous lectures also we have discussed about the position of the tetrahedral void, especially in an FCC lattice. In an FCC lattice, the tetrahedral void is along the body diagonal at 1/4 distance from the corner. So, if the corner, if you consider it as 0 0 0 coordinates, then the red colored sphere will have a by 4 a by 4 a by 4 coordinates. From this, if you calculate the AB length, then AB is equal to radius of cation plus radius of anion, like that they both are in contact, which you can get it like this, which is equal to root 3a by 4. When it is root 3a by 4, that means root 2a is equal to 4r, and also root 2a is equal to 4ra, that is along the what you call the phase diagonal. Okay. Along the phase diagonal, all the anions A is 1, then from A on the same phase diagonally, if you look at it, you have 2 other spheres, one is at the phase center, one is at the opposite corner and the phase. So, that total length will give you the 4RA, that 4RA is equal to root 2A, because that is the phase diagonal. So, now RC plus RA is equal to root 3 by 4 into 4RA by root 2. From this and also RC plus RA is equal to root 3 by 2 RA, and finally RC by RA, that is ratio of cation to anion, is equal to 0.225. 0.225 is the minimum radius ratio. Here you have to understand that the radius of cation to anion, the minimum radius ratio must be equal to 0.225 in order to have a tetrahedral void, or in other words, the radius of the tetrahedral void minimum should be 0.225 for where the cation to occupy. Then coordination number 4 or coordination number 6, square planar and octahedral. These are the 4, where in between what 4 blue colored spheres, if you look at it, they are mutually touching, and in between this space is appearing like a square, that if occupied by this yellow colored sphere, then this is what the square planar. This is RC plus RA, that is AB. AB is equal to radius of cation plus radius of anion. Now, from B towards the other blue sphere, now the line that is drawn is equal to 2RA, because that is sum of the radii of the 2 anions. Now, AB is equal to RC plus RA is equal to A by root 2. So, therefore, A is equal to 2RA, and RC plus RA is equal to root 2A, root 2 RA. Therefore, RC by RA is equal to 0.414. So, if it is 0.4, if the radius ratio, minimum radius ratio of cation to anion is equal to 0.414, then it will have the coordination number 4, and you will get a square planar void, or a cation of size, a cation of minimum size of 0.414 is the one that it occupies a square planar void as well as even octahedral void. Octahedral void also we will see it now. Now, in the coordination number 8, that is cube, all the corners are occupied by spheres. This is at the body center, red sphere is at the body center. Now, this is RC plus RA, that is equal to root 3A by 2, and also A equal to 2RA, because here we consider that both the white spheres are in contact. So, A is equal to 2RA. From this RC plus RA, you write it as root 3 by 2 into 2RA. Therefore, RC by RA is equal to 0.732. So, finally, radius ratios, if you look at it, if the radius ratio is less than or equal to 0.155, then you will get coordination number 2. If it lies between 0.155 to 0.225, as previously we have calculated, the minimum radius ratio of 0.155 is what we consider it for coordination number 3. right. If it is exactly equal to 0.155, it is most probably 2. Otherwise, if it exceeds 0.155, but below 0.225, then the coordination number will be 3. Then 0.225 to 0.414, the radius ratio will be normally 4, and that is what we call tetrahedral. 3 is the one if it is just very close to 0.225. 2, even though we mentioned, but it is very difficult, 2 will not be obtained. So, in general what we can say is 0.225 to 0.414, if the radius ratio exists, then it is the tetrahedral void that is likely to occupy, and 0.414 to 0.732 is square planar if the coordination number is 4, octahedral if the coordination number is 6, and 0.732 to 0.909, it is body centered cubic crystal, right. So, this is the radius ratio rules and the possible coordination number or possible type of the void. So, here basically when we discuss about FCC lattice and all, mostly what we are interested is in tetrahedral voids and octahedral voids. So, this radius ratio of tetrahedral void and octahedral void, the minimum requirement should always be in our mind. At the same time, the other one also what we may require is the body centered cube, because cesium chloride type of crystals will have the body centered cubic crystal, right. Now, we will go to the structures of ionic compounds. Now, let us look at the structures of some of the ionic compounds. First, let us start with the sodium chloride type. This is what we call rock salt. Rock salt type. In the rock salt type, that is NaCl type, chloride ion being the larger one, chloride ion will form the FCC lattice. That means, chloride ions or the positions of chloride ion, the lattice points of chloride ions are at corners and face centers, and face centers. Therefore, the effective number of chloride ions per unit cell, number of effective chloride ions per unit cell is equal to corner 8 into 1 by 8 plus face center 6 into 1 by 2, that is equal to 4. Now, coming to sodium ions. Sodium ions occupy all the octahedral voids, because the size of sodium ion to chloride ion ratio, radius ratio is around 0.53. Okay. R plus by R minus is about 0.53. So, 0.53 indicates that this is octahedral void, any octahedral, because octahedral void is 0.414 to 0.732. This is in this range. Therefore, sodium ions occupy all the octahedral voids, and octahedral voids are totally, now octahedral void means it is at the body center and edge center, or even other words, the number of octahedral voids is equal to effective number of atoms. So, this is equal to body center 1 plus edge center 1 by 4 into 12, that is equal to 4, right. So, therefore, total number of ion pairs, number of effective ion pairs per unit cell is equal to 4. So, the formula is Na4Cl4 implies average formula unit is NaCl, average formula. So, per unit cell you have 4 ion pairs of sodium and chloride. So, formula unit, now average formula unit will be NaCl. Okay. Then what is the coordination number of sodium ion and chloride ion here and how they have been arranged? Now, let us see by picture. Now, in this rock salt type, so as we told, there are 4 ion pairs per unit cell that exist. So, it is actually like, if you look at it, in a cube. The chloride ions are at the corners of the cube. These are all chloride ions, and they also are at, here you have a chloride, this is also chloride ion, all these are chloride ions. Sodium ions are at edge centers, these are sodium ions. These are all sodium ions, and one sodium ion is at the body center. So, like this phase center chloride ions, of course, all I am not drawing here, but in every phase center there will be a chloride ion like this. So, in total if you count, you will get number of chloride ions is equal to 14, sodium ions will be 13, because 12 edge centers and 1 body center. Here these are 8 corners, 8 plus 6, and these are 12 plus 1, and now in this coordination number, as you look at it, suppose if you consider that the ion at the body center, then this is in contact with the 6 chloride ions, this is in contact with this chloride ion, right. So, this sodium ion is in contact with this chloride and this chloride, this chloride, this chloride. So, 4 and 1 chloride ion in front face and 1 chloride ion in the back face. So, overall the coordination number for chloride ion is 6. Similarly, I mean this is for sodium ion is 6. Similarly, if you look at 1 chloride, the coordination number for chloride ion, this particular chloride ion, suppose if you consider, if you consider this chloride ion, this is at the corner, from that corner you can draw 6 faces, and your sodium ions are at the edge centers. So, 6 edge centers with which it will be in contact, like this chloride ion is in contact with this sodium ion, and here you will have 1 sodium ion, this is in contact, right, 2, and like this here you will have 3, behind 4, and top 5 and bottom this is 6 one. So, like this each chloride ion is in 6, and so for sodium ion it is 6, and for chloride ion also it is 6. And the rule also that it exists is that here you will have these 4, this is 1 sodium ion and chloride ion are always in contact. This we cannot take, because here all these 3 chloride ions are not mutually touching, because they being the chloride ions, they will repel. So, they will not be touching. So, along the body, normally in the FCC lattice means we consider these 3 spheres is touching, but in this case these 3 spheres are not touching. These 3 spheres means 2 chloride ions and 1 sodium ion along the edge that they are in contact. So, here what happens is 2Rc plus Ra is equal to, this is Ra, Rc, Rc, Ra, right. 2Rc plus Ra is equal to A, that is the edge length. This is the rule that it follows, but not, this is very important to remember, but not 4Ra is equal to, or rather 4Ra is not equal to root 2A. This is not correct, this is not valid, only this is valid in this case, but usually in FCC means this is a valid relation we take, but in this case it is not valid, this is valid. Now, so the coordination number is 6, and this is the rule that it follows. Now, for this packing fraction is equal to volume of all these spheres. All these spheres means here you have sodium ions as well as chloride ions, and effective 4 into 4 by 3 pi R Cl minus cube plus 4 into 4 by 3 pi R Na plus cube, because you have got 4 sodium ions and 4 chloride ions by A cube, that is the volume of the cube. This will be the packing fraction. Now, in usual FCC lattice, that is chloride lattice, if you take, the packing fraction will be 74. Now, in between, so only chloride ions if you take, packing fraction will be 74, 74.08 exactly. But if you do, because your some octahedral, this is nothing but your octahedral void, all the octahedral voids are occupied even at the body center. So, more packing is made. So, now what is the situation? If you take only chloride ions lattice formed by only chloride ions, then your octahedral voids as well as tetrahedral voids both are empty. But now octahedral voids are filled by sodium ions. As a result, what? Only tetrahedral voids are what? Empty. So, some of this space is now more occupied by sodium ions. As a result, the total volume of space occupied by any of the ions, either chloride ion or sodium ion, in total increases. So, this if you calculate, you get this up to 78%. 74% is somewhat closely equal to 78%. So, the packing fraction is increased. Why is it increased? Because some of the voids are occupied by sodium ions. What voids? Octahedral voids are occupied. So, this is how we can calculate the packing fraction, as well as also we can calculate the density just from mass by volume. Mass again you will take this and volume is again this. See, also what you can calculate is the density, right. Now, here another possibility of asking the questions is that what are the nearest neighbor, how many nearest neighbors that a chloride ion can have? Nearest neighbor, nearest neighbor is nothing but, first nearest neighbor is nothing but coordination number. That means, how many sodium ions surrounding one particular chloride ion, or how many chloride ions surrounding a particular sodium ion, that is coordination number is also nothing but called as nearest neighbor, and that is the first nearest neighbor. What is the second nearest neighbor? If this is the first nearest neighbor, then obviously the second nearest neighbor is this, right, one chloride to the other chloride. Now, this particular chloride ion is surrounded by how many such chloride ions? Because here you will get this as the 8. So, the number of chloride ions, because from this corner you can have 8 such cubes, and in every case you will get one chloride ion like that. So, then it will be 8. So, one chloride ion, this is the nearest neighbor because they both are in contact, but these two are not in contact. There is a gap in between, right. So, how many such chloride ions you can have surrounding this particular chloride ion? You can have 8. What is the third nearest neighbor? The third nearest neighbor will be, so this is first nearest neighbor, this is second nearest neighbor. Then the third nearest neighbor will be the ion that is present at the body center, that is sodium ions, that is again 8. So, like this, what is the first nearest neighbor? First nearest neighbor means that are in contact. Second nearest neighbor, little distance, means what is the second nearest? Third nearest, depending on the positions we have to count them. This more clearly we can see in these slides. In this slide, for ionic compounds of the general formula of Ax By, the ratio of the coordination number of A to that of B will be, the ratio is y:/x. Then rock salt, this NaCl is what we have discussed just now, right. The white ball is chloride ion, red ball is sodium ion if you consider. Then this is what the FCC lattice, all the chloride ions are at corners and face centers. So, if you count them, then you will get it as 14, and sodium ions occupy octahedral voids, that is at the edge center and body center. These sodium ions, now if you count, you will get it 13, right. Now, number of chloride ions per unit cell with respect to the contribution of each chloride ion at the corner and face center, if you do as already we have done, we will get it as 4. Sodium ions per unit cell also we get 4. Formula is therefore NaCl. Coordination number of Na plus is 6. Chloride ion is also 6, right. Then other compounds which have this kind of structures are all halides of alkali metals except cesium halides, that is sodium chloride, potassium chloride, potassium bromide, sodium bromide, okay, even rubidium bromide, rubidium chloride, all this, and halides of alkaline earth metals, again except beryllium oxide, AgCl, AgBr, AgI, all this will have the similar kind of structure. This is how it appears. This is the adjacent unit cell for the same. Now, this is a one particular plane, this is another particular plane. So, here this is, now first we considered that chloride ions are occupying the lattice and sodium ions are occupying the voids, octahedral void. Now, unit cell, as in the beginning we told, can be taken from chloride to chloride, or even you can take from sodium to sodium. So, if you take a unit cell from sodium to sodium, as we are observing over here, those dotted lines are drawn from one red ball to another red ball, that is from sodium ion to sodium ion. Now, it appears like this. So, now in this, if you look at it, what it appears is sodium ions are at the corners and also at the face centers. So, it appearing as if that sodium ions are forming the lattice and the chloride ions are at the edge center and body center. Therefore, now in this case, the sodium ions will be 14, chloride ions will be 13, but overall this is the case. So, consider the unit cell with chloride as FCC. Now, this is A equal to 2R plus 2R minus, that is what already we have written. This is the phase diagonal, root 2A equal to 4R Cl minus, but this is not correct as such in general. So, consider the unit cell with sodium ion FCC, this is the one. Now, in this case, A dash is equal to 2R, whether it is A 2R Cl minus plus 2R Na plus. Now, in this root 2A equal to 4R Na plus. Now, comparing R Na plus is equal to R Cl minus. Similarly, any alkaline metal is equal to any halide. After rock salt, now we discuss about zinc blend, ZNS type. ZNS type. Now, whether it is rock salt or ZNS, all these are AB type crystals. A is cation, B is anion. One cation, one anion. Average ratio is 1:1. So, AB type is generally what we are discussing. So, in this zinc blend type, now here sulfide ion forms FCC lattice. Sulfide ion forms FCC lattice. Sulfide ions will form the FCC lattice. So, here sulfide ions you will get again 14 in number, because corners plus face center. Zinc ions occupy tetrahedral voids. Tetrahedral voids alternatively, not all the tetrahedral voids, only alternate tetrahedral voids. So, that means if we consider a cube, then all these are occupied by again by sulfide. Sulfide ions are at the face centers, right, front face, back face and all that if you take. Then zinc ions are at the tetrahedral void. So, now in an FCC lattice, how many tetrahedral voids we will have? Number of tetrahedral voids is equal to twice the number of effective atoms, that is twice the rank. For an FCC lattice, the rank is 4, that is effective number of atoms is 4. So, number of tetrahedral voids which is twice to that obviously will be 8. Now, here alternative tetrahedral voids. So, here you will have 4 zinc ions. Now, where the 4 zinc ions will be? Now, from this if you draw a body diagonal, now as we told if this is 0 0 0, then a tetrahedral void will be formed at A by 4, A by 4, right. From here along this body diagonal you will have 2 tetrahedral voids. Now, from this body diagonal again you will have one more, here you will have one, from this body diagonal you will have one, right, and then from here to here, here to here, here to here, these are the 3, and total on the other side again you will have 1, and this front and back which we are not able to do here, you will get along each body diagonal, at 1/4 distance, A by 4, A by 4, A by 4, from the corner at a tetrahedral void, zinc ion is present. Along each body diagonal. So, along each body diagonal, here you will have one, here you will have one, but it will be present only at one place. So, the number of tetrahedral voids will be 4. So, here what happens? The coordination number for zinc ion, because here zinc ion is at the tetrahedral void. When zinc ion is at the tetrahedral void, means 4 sulfide ions. So, it is 4, and for sulfide ion, as you can see, this is a sulfide ion. Now, this sulfide ion, from this corner you can draw 8 body diagonals, one body diagonal to this, one body diagonal like this, and all the 8 cubes that we can draw from this corner. From this corner we can draw 8 cubes. At each of the cube you will have one body diagonal. So, this corner is common to 8 such body diagonals, but all body diagonals will not have tetrahedral voids, only alternate. So, if this has, then this body diagonal will not have, then this body diagonal again will have. So, like that, out of 8, alternatively if you place zinc ions, you will have 4 zinc ions surrounding this particular sulfide ion. So, for sulfide ion also the coordination number is 4. Coming to effective number of atoms, this is already 4 and this is 4. So, the formula is Zn4S4, which is equal to Zns, right. So, this is how a zinc sulfide structure will be formed. This we can have more clarity once if we look at the slides. Now, look at the zinc blende structure. Now, white spheres are again sulfide, red is zinc. Now, these are the sulfide ions at the corners and face centers. Zinc ions occupies alternate tetrahedral voids. So, that is along the body diagonal, that is 1. This is from the other body diagonal, right. This is from the third body diagonal, this is from the fourth body diagonal, right. Now, that each red sphere, if you look at it, each red sphere is at the tetrahedral void formed from one corner and 3 face centers, one corner and 3 face centers. So, that one corner and 3 face centers is nothing but one tetrahedral void, right. So, number of sulfide ions per unit cell is 4, zinc ions is 4, formula is Zns, and coordination number for zinc is 4, sulfide is also 4. So, this easily you can understand that each red ball is in contact with 4 spheres, one is at the corner, 3 are at the face centers, and one sulfide ion is in contact with 4 zinc ions which are placed at each tetrahedral void, alternate tetrahedral void, and the other compounds with the similar structure is beryllium oxide, that again will have the similar structure. Now, we will go to the fluorite type. Now, we go for AB2 type. Earlier what we have seen is AB, that is 1:1 ratio of cation to anion. Now, it is 1:2 ratio of cation to anion. CaF2 is the first example, CaF2, that is fluorite is what we call fluorite type. in this fluorite type, what happens is the cation calcium ion forms FCC lattice. So, this is again 8 into 1 by 8 plus 6 into 1 by 2, that is again equal to 4. Fluoride ions occupy all the tetrahedral voids. So, when you are having all the tetrahedral voids, then it is the number is that is equal to 8. Okay. So, now therefore, the number of cations to anion. So, calcium ion to fluoride ion number ratio is 4:8, that is 1:2. Therefore, formula is 1:2, that is CaF2. And when it comes to coordination number, for fluoride ion is obviously 4 because it is at the tetrahedral void. For a tetrahedral void, the coordination number is 4 because 4 spheres are existing. A tetrahedral void is formed from 4 spheres. But for calcium ion, when it comes from each, when the calcium ion is present at the corner, from each corner you can have 8 other cubes and 8 body diagonals as well. As here the fluoride ions are present at all the tetrahedral voids, unlike the previous case. In the previous case it was alternate, so it was the coordination number was 4. But now in this case all the tetrahedral voids are occupied. When all the tetrahedral voids are occupied, then the coordination number will be 8 for calcium ion. In the previous two examples, the coordination number for anion and cation is the same, but in this case the coordination number for fluoride is 4, but for calcium is 8. In fact, that also you can understand by charge balancing that this is a dipositive cation and this is a uninegative ion. So, obviously for the charge balancing, the coordination number around the calcium, you should have the twice the number of atoms as the number of other ions for the fluoride. Therefore, the formula is CaF2. Okay. So, here again the packing fraction, density and all that you can determine in the normal way that we did it for sodium chloride, and this more clarity again we can get it from the slides. Let us look at the fluoride structure. Calcium ions, fluoride ions. Calcium ions, as I told, calcium ions here cation. In the previous examples, anion will form the lattice, but here the calcium ion being larger than the fluoride ion, calcium ions will form the lattice, FCC lattice, that is corners and face centers, you can see, and all the fluoride ions are at the tetrahedral voids, all of them are completely inside. From each corner, if you look at it, you will have one sphere, white sphere, and that white sphere is nothing but the one that is at tetrahedral void of, again the tetrahedral void is from one corner and 3 face centers. Okay. Then number of calcium ions per unit cell is 4, fluoride ions per unit cell is equal to 8. So, the formula is calcium CaF2. Coordination number for fluoride is 4, calcium is 8. As you can see there that each fluoride ion is surrounded by 4 calcium ions. So, that the coordination number is 4. Each calcium ion is surrounded by 8 fluoride ions. So, the coordination number for calcium is 8, and each fluoride is surrounded by 4 calcium ions, and so the coordination number is 4. And the other compounds having this kind of structure as vanadium dioxide, thorium dioxide, lead dioxide, mercuric fluoride, etc. Most of the transition element oxides, dioxides and fluorides will have this kind of structure. Okay. Next we have to go for antifluoride structure. In antifluoride, that is lithium oxide type is what we call it. It is just opposite to the fluoride. In the fluoride, calcium ions are cations forming the lattice and anion occupy the voids, but in this case oxide ion being larger than the lithium ion, oxide ion will form FCC lattice. So, this is now 8 into 1 by 8 into 6 into half, that is equal to 4, and lithium ions occupy all the tetrahedral voids. So, that is again equal to 4, and here therefore, formula is, so the ratio of lithium to oxide ratio is 8:4, all the tetrahedral voids. So, it is 8. So, it is 8:4, that is 2:1. So, the formula is Li2O, and coordination number for lithium ion is 4 and for oxide ion it is 8. Just like opposite to the previous case, there the coordination number for calcium is 8, for fluoride it is 4. Now, for the cation it is 4 and for the anion it is 8. Okay. Now, this exact structure as already we have seen for calcium fluoride, here it is exactly opposite, but that once again for more clarity we see the slide. In this antifluoride Li2O, white balls are oxide ions, red balls are lithium ions. The lattice is by oxide ions, 14 oxide ions at the coordinates and phase centers. Lithium ion occupies all the tetrahedral voids, exactly again the same way, only the name is changed, but the positions, colors and everything is same as the previous case. Number of oxide ions per unit cell, if you count it out, effective number of oxide ions you will get them as 4. Lithium ions effectively you will get 8, and so therefore, the formula is Li2O. Coordination number for lithium is 4, for oxide it is 8, and the other compounds having this kind of structure are sodium oxide, potassium oxide, rubidium oxide. So, in fact, it is nothing but except the cesium oxide, all oxides of alkali metals are having the same structure of antifluoride. The next what we go is for cesium halide. Next is the cesium chloride type. This is again AB type only, but the difference is this is BCC structure. Earlier AB what we have discussed is the lattice is the FCC lattice, but this is now BCC lattice. Here cesium ions are at the corners of a cube and chloride ions are at the body center, because cesium ion being very large, the ratio of cation to anion or the vice versa, anion to cation, either way you can consider it, like in the previous examples we have seen that it is about 0.8. So, anything between 0.732 ratio of cation to anion, 0.732 to 0.999, this is BCC, and here cesium ion being very large, chloride ion being small. So, here the radius ratio is relatively more, therefore, it forms a body center, and so here all chloride ions, these are all chloride ions, this is your cesium ion. So, Z effective for chloride is 8 into 1 by 8, or even you can take the vice versa. Cesium ions are at the corner, so you can consider this as cesium ions, either way you can take, that does not make any difference. and then this is the chloride ion. Then Z effective for chloride ions is, as it is completely inside the cube, it is completely inside the cube, that is at the body center. So, it completely belongs to that particular unit cell. So, effective is chloride is 1, for cesium it is 8 into 1 by 8, that is also equal to 1. Therefore, formula is what? The formula is cesium chloride, and here these are in contact. So, here 2R plus 2R minus 2R plus 2R minus twice the sum of the radius of cation to anion is equal to root 3a. This relation is what we have seen. These three are in contact. Therefore, here coordination number for chloride is 8, for cesium also it is 8, because if you consider this cesium ion, this chloride ion is at now. So, here this is the cesium ion and here you are keeping the chloride ion, this is your octahedral void. So, when this is cesium ion of one layer and at the center what you have is chloride ion, again if you keep another 4 like this, then of course these two are not in contact. So, then what you will get is a coordination number 8 for each one, and this is how you, now here you can measure the packing fraction and density as well, and this is the relation what it exists. This again, let us see the diagram in the slideshow. So, for the cesium halide, this is a chloride ion, cesium ion, this is a cube, chloride ions will form the primitive, chloride ions form the primitive, cesium ion occupy the center of the unit cell, that is the body centered cube. So, number of chloride ions per unit cell is equal to 1, cesium ions also equal to 8 into 1 by 8, that is 1, formula is CaCl, coordination number of cesium is 8, chloride is also 8, and other compounds having the similar kind of structures are all the halides of cesium and ammonium. That means, cesium chloride, cesium bromide, cesium iodide, ammonium chloride, ammonium bromide and ammonium iodide, the other compounds that will follow the similar structure. Then next let us go for corundum. Next let us see corundum structure. In the corundum, that is Al2O3, it is different from all the previous structures what we have discussed. In all the previous structures, the lattice is FCC lattice or rather cubic lattice. In the cesium chloride, it is a primitive cube, and in the case of sodium chloride, zinc sulphide, calcium fluoride in all, it is the FCC lattice. That is, but overall they are all the cubic lattices. But now in the case of corundum, Al2O3, the lattice is formed by oxide, and the lattice is not face centered lattice, it is hexagonal lattice, hexagonal primitive unit cell, that is the lattice. That means, all the oxide ions are at the corners of the hexagon, two opposite face centers, and then also you have 3 completely inside. So, as a result, what for a HCP unit cell, the effective number of atoms in the lattice is equal to 6. So, that if you look at it, the diagram that is given over here, the black circles are the oxide ions of one layer, broken blue circles are the oxide ions of the second layer. Then by the combination of 3 mutually touching spheres of layer 1 and layer 2, you will get one octahedral void. That octahedral void is the one that is shown with this green and the other orange color small circles. Now, first of all, that overall lattice, if you see, that is a hexagon, that is shown with the red lines, hexagon. Now, oxide ions form this unit cell, and aluminum 3 plus ions are present at the 2/3 of the octahedral void. Means, out of the 3 octahedral voids that are formed over there, one is the green and 2 are the orange. The 2 orange colored ones are actually the Al3 plus ions. one is remaining vacant. So, from this if you look at it, the formula will be, because oxide ions per unit cell, how many oxide ions per unit cell we will get? It is, the total number is 12 and effective number, this octahedral voids also what we will get is the 2/3. So, the 2/3 of that will be equal to then 6, then it is equal to Al2O3 will be equal to, so number of oxide ions per unit cell is 2, Al3 plus ions per unit cell is 4/3. So, the formula will be Al4/3O2, that is Al4O6, which is an average becomes equal to Al2O3. Coordination number of aluminum 3 plus as being it is at the octahedral void. So, it is 6 because the coordination number for an octahedral void is 6. What is an octahedral void? Formed by a set of 6 spheres. So, coordination number will be 6 and coordination number for oxide is 4. Okay. And overall the other compounds that can have this kind of structures are Fe2O3, Cr2O3, Mn2O3, etc. This is the corundum structure. And after the corundum structure, then what also we have is rutile, titanium dioxide. The titanium dioxide, oxide ions again forms hexagonal primitive and half of the octahedral voids are occupied by titanium ions. So, this is again hexagon like in the previous case what we have seen, and here this is the octahedral voids, half of them are being occupied. So, number of oxide ions per unit cell is equal to 2, number of titanium ions per unit cell will be equal to 1. So, the formula will be TiO2, okay. And coordination number of titanium 4 plus ion is 6 and oxide ion is 3, right, as you can see in the picture very clearly. And the other compounds that will have this similar kind of structure is manganese dioxide, tin dioxide, magnesium fluoride and nickel fluoride. The next is a perovskite. This is calcium titanate. In the calcium titanate, what happens is the oxide ions will form the FCC lattice. This is the divalent calcium ions. Titanium ions will form the, occupies the center of the unit cell. Titanium is at the body center, right, and oxide ions occupy the face centers. Oxide ions are at the face centers, calcium ions are at the corners of the primitive cubic unit cell, and titanium occupies the center of the unit cell. So, number of oxide ions per unit cell is 8 into 1 by 8. Number of oxide ions, number of oxide ions are 3 because they are at the face centers. We have 6 faces and contribution is half. So, 6 into half it is equal to 3. Calcium ions per unit cell is equal to 1, that is because 8 into 1 by 8 that is equal to 1, and titanium ion is at the center of the cube. So, that is also equal to 1. So, the formula is CaTiO3. Okay. This is what we call perovskite. Coordination number for oxide is 6, for titanium it is 6 and for calcium it is 12. As you can see that each one is in contact with how many other different colored spheres, from that easily you can understand. And next is the simple and inverse spinel. In the spinel, oxide ions will form the FCC lattice, magnesium ions will occupy 1/8 of the tetrahedral voids. Tetrahedral voids how many will have? Tetrahedral voids is equal to twice the effective atoms. Here oxide ions form the FCC lattice. So, effective number of oxide ions is 4, 1/8 of the tetrahedral void. So, that means 1/8 into 8 that is equal to 1, half of the octahedral voids. Octahedral voids are 4, half into 4 that is 2. So, the oxide ions per unit cell is 4, magnesium ions is 1, aluminum ion is also 1. So, in total what you will get is MgAl2O4. Inverse spinel, oxide is FCC, divalent 1/8 of the tetrahedral voids, trivalent is 1/4 of the octahedral void or 1/8 of the tetrahedral void. So, oxide ions per unit cell is 4, divalent per unit cell is 1, trivalent per unit cell is 1, and finally, it is all equal to Mx2O4. Okay.